The first definition is a frequency distribution or frequency table. A frequency table shows how data is partitioned among all of several categories or classes by listing all of the categories along with the number of data values in each category. I make a frequency distribution every time I give a test and I grade those tests. I list how many A's, how many B's, how many C's, how many D's, how many F's. Or I could break it down into numbers. My first class would be 90 to 100. My second class would be 80 to 89 and so on. And then I just tally up how many grades are in each group to see overall how the class did. So that is a very quick example of a frequency distribution. When you look at this data, pulse rates of females and males, I can't make any sense of that data. I mean, it's just a bunch of numbers. I don't know what the numbers mean. I don't know, well, I know what the numbers mean. They're pulse rates. But I don't know if the males and females in this group had a high pulse rate, a low pulse rate, an average pulse rate. You can't really get a picture of the distribution of that data without organizing it somehow. And a frequency distribution is one way to organize it. This is a frequency distribution of that data. These are called the classes, 60 to 69 beats per minute, 70 to 79 beats per minute, and so on. And then somebody just went through that list of data and using tally marks, just put a tally mark every time they found one of the data values lying in each class. And at the end, just count up how many tally marks are in each class. When you look at the frequency distribution, you have a much better understanding of what that data is telling you. Most folks' pulse rates fell in the range of 70 to 79. Second most was 60 to 69. So at least for this group, if not for the entire population, because we don't know if this group is representative of the entire population or not, but at least for this group, the vast majority had pulse rates between 60 and 79. Very few had pulse rates below, not below, but above 90. Very few had pulse rates above 90. So it's just a way of organizing information to make it easier to understand. Now, here are the terms that you need to know about frequency distributions. The lower class limits are the smallest numbers that actually belong to the different classes. So these are your lower class limits right here. The 60, 70, 80, 90, 100. Your upper class limits are the largest numbers that can actually belong to different classes. So the 69, 79, 89, 99, and so on are your upper class limits. Those words make sense. Lower class limit, upper class limit just tells you the boundaries for each class. And then there are class boundaries, the numbers used to separate classes, but without the gaps created by class limits. Every pulse rate listed on that original table fell into one of these classes. There was no pulse rate that was, say, 69.5 because nobody can have half a heartbeat. But if we were going to make a graph of this information, it might be helpful to have the numbers that are separating the classes, maybe the average of an upper class limit and the next lower class limit. The average of 69 and 70 would be 69.6. 69.5. So 69.5 would be a good demarcation between those two classes. 79.5 would be directly in the middle of those two classes, 89.5 between those two classes. Those are the class boundaries that we would probably use if we were making a histogram, which we're going to talk about in a minute. Notice that you always have one more class boundary than you do classes. Think of these class boundaries as fence posts. separating the classes. This frequency histogram has, or not histogram, frequency distribution has 2, 4, 6, 7 classes. It has 8 boundaries because you have to have a left fence post and a right fence post in addition to the 6 fence posts between classes. So anytime you're listing the class boundaries, you're going to have one more class boundary than you have class because of that left and right fence post. Class midpoints are the exact middle values of each class. You can find a class midpoint just by adding the upper and lower limit of each class and dividing by 2. It's the average of 60 and 69. The average of 60 and 69 is 64.5. So that's the first class midpoint. And similarly, did I say 0.9? I didn't mean 0.9. I meant 64.5, but I'm not sure what I said. I just thought of something you may want to write down on class boundaries because I didn't type it for you. If you want to make a note about how to find the class boundary right here, let's see, the best way to word it, add an upper limit of one class and the lower limit of the next class, and divide by 2. What's happening? Did you find this slide?
No, I've got 2.1 terms. So I'm trying to figure out.
That is tomorrow's. That's not even today's. That's okay. 2.4. Okay. That's 2.4. So just pull that out. I'm not sure how it got in there. No, it's okay. Stop it. Okay. Stop apologizing. Yes. Yeah. No, it's okay. You add an upper class limit to the lower limit of the next class and divide by 2, which really makes sense if you think about what boundary is. It's halfway between one upper limit and the next lower limit, halfway between 69 and 70, halfway between 79 and 80, halfway between 89 and 90. That's what the class boundaries are. All right, I just realized that I had not typed how you find the class boundaries. I did type how to find the class midpoints. Just add the lower and upper limits of a class and divide by 2, again, because you're looking for the average of 2 numbers. The class midpoints, they're in red, and the class width. The class width is the difference between 2 consecutive lower class limits or 2 consecutive upper class limits, the difference between 60 and 70 or 69 and 79. We would say these class widths are 10. As if I were tallying up grades on a test, I would use 90 to 100 for one class and 80 to 89 for another class, 70 to 79 for another class. Each of those would have a class width of 10 points. Yes. Yeah. Class midpoints are smack in the middle of each class. So you're going to have the same number of class midpoints that you have classes. The class width should be the same for every class. It's the class boundary that you're going to have more of. And if you think about the fence post, got to have one on the left, one on the right, and then those in the middle, you'll see why you have to have one more class boundary than the number of classes. All right, constructing a frequency distribution. Here are some steps, and then we're going to practice it. Determine the number of classes. That's up to you. But it'll depend on how spread out your values are. If I have grades from 0 to 100, it makes sense to divide that up into maybe 10 classes. Maybe I don't want to lump all the Fs together because there's a big difference between a person who made 55 and a score of 15. So maybe I'll use 10 classes and tally marks for everybody who made 0 to 10 and 10 to 19 and so on. Determine how many classes should be between 5 and 20, just because if you have 100 classes, that's going to be as difficult to make any sense of as the original data was. That's just too many classes to really get an image of what the data looks like. The class width, just think about test scores again. The highest test score minus the lowest test score and divide by the number of classes. If I decide, if I have grades from 0 to, well, let's say I just have grades from 10 to 90, then the range of that data is 80, which you get by subtracting the 10 from the 90. If I've decided to make that into 9 classes, I would say 90 divided by 9, and my class width would be 10. Choose the minimum data value or a convenient value below it as the first lower class limit. If I had scores from 10 to 90, then 10 would be my lower limit of the first class. And then to get the lower limits of all the other classes, you can just add the class width. List the lower class limits in a vertical column, proceed to enter the upper class limits. And then just start tallying into which class each data values fall and count up your tally marks. Let's do an example because that makes much more sense. Let's make sure you understand the terminology first. You have some problems in the homework that just say identify the class width, the class midpoints, the class boundaries, and then you have some where you actually have to make the table. This first problem gives the weights in pounds of discarded plastic. I think that is maybe per household per week. And the frequency would be the number of households who had that many pounds of trash per week. So identify the class width. That's just the difference between each lower class limit or the difference between each upper class limit. What's the difference between 0 and 1 pound of trash, or 1 pound of trash and 2 pounds, or 2 pounds and 3 pounds? Just 1. So the class width is 1. Units always make more sense. I don't think they'll ask you for the limits in my math lab, but that does make it clear that you understand what it is we're talking about. The class width is 1 pound. Class midpoints, how many classes do I have here? 6, so how many class midpoints? 6, because each class has a midpoint. There's something exactly halfway between 0.00 and 0.99. Something exactly halfway between 1.00 and 1.99. How do you find the class midpoint, say, of this first class? Yeah, you're looking for smack in the middle, the average, add and divide by 2. So 0 plus 0.99 is just 0.99. 0.99 divided by 2, 0.5. This doesn't do so well in my head. 0.495. Isn't that right? 0.495 would be the first class midpoint. And it's right here. That's what we're talking about. Halfway in between the lower and upper limits for that class. Now we could continue doing that. For the second class, we could add 1 plus 1.99 and divide by 2, then 2 plus 2.99 and divide by 2, but you don't have to. If you know the class width is 10 and the first class midpoint is 0.495, what's the next one going to be? 1.495. Did I say the class width is 10? I need to just slow down and breathe. Class width is not 10. We wrote 1 right here. I'm just saying 10. Sorry. The class width is 1, so just add 1 to get the next midpoint. Add 1 to get the next midpoint after that. The second midpoint would be 1.495. The third midpoint would be 2.495. Go ahead and list all 6. Let me write them down and then you ask that question. 0.495, 1.495 is the midpoint of the second class. 2.495 is the midpoint of the third class. 3.495 is the midpoint of the fourth class. Then 4.495 and 5.495. Yes, ma'am.
Okay, so when you're trying to get the midpoint between 0.000 and 0.099, would you begin adding it at 0.01?
No. Let's think about easier numbers for a second. If I was going to use from 80 to 90 for one of my classes when I was tallying up grades, I would just add the 80 plus the 90, which is 170, and divide by 2. 85 would be the class midpoint. All right. So you just add the lower limit to the upper limit for each class and then divide by 2 to get what's exactly in the middle of the upper and the lower limits. All right. But you need to have the mental image of what a class midpoint is. It's exactly what it sounds like. It's smack in the middle of each one of those classes. And then the class boundaries are the fence post between the classes. How can I find what's exactly halfway between 0.99 and 1? Add and divide by 2. That's how you find the average of any two numbers. 0.99 plus 1 is 1.99. You can think of this as 99 cents and $1. What would be halfway between 99 cents and $1? Well, yeah, 99.5 cents written as a decimal would be 0.995. So that's one of the boundaries right here. 0.995 separates those first two classes. And you could continue adding the upper limit of one class and the lower limit of the next class and dividing by 2. But you don't have to. Again, if you know the class width is 1 and this class boundary is 1.99 or is 0.995, what's this fence post going to be? Yeah, 1.995 is halfway between $1.99 and $2. 2.995 is halfway between 2.99 and $3. And 3.995 and 4.995. However, if I'm building a fence to hold in these 6 cows, how many fence posts is it going to take? Not just these 5 that separate the cows, but got to have one on the left and one on the right. So just go back one more and up one more. What would be one before 0.995? actually be negative 0.005, and it doesn't make sense to talk about a negative pounds of trash. So for this left fence post, you would actually just use 0, only because a negative pounds of trash doesn't make sense. If this were temperature, I could go back to a negative. And what should this right class boundary be? Well, the distance between the class boundaries need to be the same. So if the last one we had was 4.995, the one on the right would be 5.995. So the difference between all of these class boundaries is 1, except for this one on the left, because it didn't make sense to talk about a negative. And that's the 7 fence posts it would take to separate those 6 cows. And I'm not going to rewrite all those class boundaries, but it's that list. All right, like I said, you have a few problems that just say list the class width, list the class midpoints, and list the class boundaries. And then you have a problem where you actually make a frequency distribution. You'll always be given the lower class limit, what to start with, and the class width. This table has to do with the amount of tar and nicotine and carbon dioxide in cigarettes. Like Tony said, made her want to quit smoking just looking at these numbers. We have, let's see, 25 brands of cigarettes, and the amount of tar, and these are filtered non-menthol cigarettes. We have the amount of tar, the amount of nicotine, and the amount of CO, I think that's supposed to be CO2, and the 2 got cut off. That's carbon dioxide. Construct a frequency distribution, begin with the lower class limit of 0.2 milligrams, and use a class width of 0.2 milligrams. Well, we're told that the lower limit of the first class is 0.2. And if the class width is also 0.2, what is the next lower limit going to be? 0.4. You're just adding 0.2 to the lower limit above. And what is the next lower limit going to be? 0.6, and then 0.8 and 1.0 and 1.2. Now for the upper limits, notice, let's see, what is it we're going to make? We're going to make our frequency just using this nicotine column. Well, let's think about it a second. All of these amounts of nicotine are listed to the nearest 10th. None of them are listed to the nearest 100th. So nothing is going to fall between 0.3 and 0.4. I don't have to worry about getting a 0.35. There is no 0.35 here. So 0.3 is sufficient for that upper limit. And then the next upper limit would be what? Hang on to that question just a second. I'll come back to it. 0.5, and then 0.7, 0.9, 1.1, and 1.3. I would do this in pencil because it is possible that you will have to erase. But I got that first upper limit by looking at this data and noticing that all of them were to the 10th place, so I don't need to have to the 100th or to the 1000th or to the 10,000th for my limits. Either it's going to be 0.3 or 0.4. There's nothing, there are not any of these values that are going to be 0.35. All right. Now, if you ask me for the class boundary, it would be halfway between 0.3 and 0.4. So 0.35 would be a boundary, but none of these values are sitting on the boundary. None of them are sitting on the fence post. All right. Now we just need some tally marks. I'm going to start this process to make sure that you understand what I'm tallying, but then I'll just tell you what I got for the other classes. Cigarette brands with amounts of nicotine between 0.2 and 0.3. Actually, that's not the easiest way to do it. The easiest way to do it is go down the list. 0.4 for Barclay cigarettes would fall in that second class. 1.0 falls in the 5th class. 1.2 falls in the 6th class. 0.8 is in the 4th. And then just go on down to the bottom of the list and make sure you have 25 tally marks. All right. To not spend class time doing that, let me just tell you there was only one cigarette that had between 0.2 and 0.3 milligrams of nicotine. Only one that had between 0.4 and 0.5. Only one had between 0.6 and 0.7. 8 fell in that 4th class. 12 fell in the 5th. And only 2 fell in the highest class. Now, it was hard to make any conclusions about this data looking at all these numbers. They were just overwhelming. But with the frequency distribution, I can say, well, most of these 25 cigarettes, almost half of the brands had between 1.0 and 1.1 milligrams of nicotine. And I could say almost all of them had at least 0.8 milligrams of nicotine. Only 3 out of the 25 had less than 0.8 milligrams of nicotine. Again, if I ask you for the class boundaries, it would be halfway between 0.3 and 0.4. Right here would be 0.35, 0.55, 0.75. But don't forget to go back a class boundary too. Let me just list those. Actually, I have on here. Where is it? Right there. The first class boundary is 0.35. The class width is 0.2. So just keep counting up by 0.2. And you can go back by 0.2 to get your left fence post. 0.35 minus 0.2 is that 0.15. All right. Any questions about that frequency distribution or the terms class width, class boundaries, class midpoint? Yes, ma'am. The 0.3, I could have used, okay, I already had this lower limit filled in for all the classes. I could have gone all the way up. I want to get really close to 0.4, as close as I need to. I could have gone up to 0.39 or 0.399 or 0.3999, but I didn't need to because all of these were to the nearest 10th. So I didn't need to go up to 0.399. I just needed the next 10th before 0.4. and the next tenth before 0.6. That was a better way of describing it, the tenth before, because all my data values were to the nearest tenth. I didn't need to go to the hundredth or thousandth. All right. We talked about frequency tables. Let's talk about, if I can, all of a sudden, I'm thinking, there we go, how to make that go away. Let's talk about a histogram. A histogram is just a picture of your frequency distribution. Some folks like to look at numbers, some folks like to look at pictures. This is just a picture of that. Notice along the horizontal axis, we would have a couple of things you can use. You could use the lower class limits, but it kind of makes sense to use your class boundaries. Again, your class boundaries are the fence posts, and you don't want anybody straddling a fence post. If I used the lower class boundaries, if I used 60 and 70 and 80 and 90 along my horizontal axis, then into which class would the 60s fall? Or excuse me, into what class would the 70s fall? Would they be on this side of the fence or that side of the fence? They'd actually be right on the fence. So it makes more sense to use your class boundaries for the horizontal axis. I'm not ready to show you that. Use the class boundaries for the horizontal axis. The vertical axis is just the frequency, the number of brands of cigarettes that fell in each class. Make sure you always label your axes so that anybody looking at your graph can understand what it's about. Yes. Yeah, because all the values will clearly fall into one class or the other rather than being on a fence post. Look at this slide. This gives you some guidelines, and then we'll do one. The bars on the horizontal scale are clearly labeled with either the class boundaries or the class midpoints or the lower class limits. It's really best to use the class boundaries. You'll see some histograms that have the lower class limits, but you're going to have some guys on the fence post, or class midpoints, but class boundaries is what we'll use. The horizontal scale, use the class boundaries or the class midpoints. The vertical scales, use the class frequency. So let's do a histogram for the milligrams of tar in these 25 cigarettes, 25 brands of cigarettes. Trying to get my frequency table and my little spot I left for a histogram both on the screen at the same time. All right. On the other handout, I had written the class boundaries, and you probably copied them down. So let's just put those across the horizontal axis, starting with the left boundary. The left boundary was 0.15, and the class width was 0.2. So just count by 0.2s. Yeah, 0.35, 0.55, 0.75, 0.95, 1.15, and the right boundary was 1.35. The greatest frequency that we had in any class was 12. So that's what needs to go up the vertical axis. Now, did I actually leave you 12 little lines here? I think I did. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep, you can count by ones. Or you can just label every other line and count by twos if you don't want to try to squeeze all those numbers in. Did you have a question? Okay. Only one brand of cigarette had between 0.2 and 0.3 milligrams of nicotine. So the bar for that class only needs to go up to the first line. Only one brand of cigarette had between 0.4 and 0.5 milligrams of nicotine. So the bar only needs to go up to 1 for that class. And the third class also had a frequency of 1. The fourth class had a frequency of 8. Its bar is much higher. The next class had a frequency of 12. And the last class had a frequency of 2. So if you're a numbers person, you can look at the frequency distribution table. If you're a picture person, look at the histogram. Both of them confirm that most of those 25 cigarettes, and I don't know if those 25 brands are representative of the entire population of cigarettes or not. I don't know. I don't know how they were chosen. But at least of those 25, certainly the vast majority of them had, like we said up here, 0.8 or more milligrams of nicotine. And nicotine is what you get addicted to. I don't think you get addicted to the tar or the carbon dioxide, but the nicotine is what's very, very addictive. So, Tony, if it doesn't cause you to quit, at least smoke these. No. Just quit. Okay. Okay. We'll have a quitting party. I think that's awesome. All right. So we've talked about a frequency table. We've talked about a histogram. Now we need to talk about another kind of table, a relative frequency distribution. The relative frequency distribution includes the same class limits as a frequency distribution, but the frequency of a class is replaced with the relative frequency of the class as a proportion or as a percent. Maybe instead of wanting to know just how many people had pulse rates between 60 and 69 and how many have pulse rates between 70 and 79, maybe instead of how many, we want to know what percent. What percent of people had pulse rates between 60 and 69? What percent had pulse rates between 70 and 79? If we knew that 12 people fell in this class, how could we find what percent of the total that is? by the number of people. Let's see. I don't know if we were told how many people that was. 40. That's 40 people. So 12 divided by 40 would give us the percent in this class. 14 divided by 40 would give us the percent in this class. Yes. Yes. Or you could have counted how many numbers were given to you on the initial data table. But since you already have the frequency distribution, just add up all the frequencies. So here was our frequency table for the pulse rates. Here's our relative frequency table for the pulse rates. It's just these values, each of those values divided by 40 gives you the percent of individuals that fall in each class. So we can do the same thing with our cigarettes. I recopied the frequency histogram here because I didn't want to have to flip my page back over to look at it. These are the same classes we had from the previous page. These are the frequencies we had from the previous page. How many cigarettes were in this study? 25. You can either count how many were on the original table or just add up those frequencies and you get 25. So what percent of the cigarettes fell in the range of 0.2 to 0.3 milligrams of nicotine? 1 out of 25 is 4%. Just punch on the calculator, 1 divided by 25, and then change it to a percent by multiplying by 100 or moving the decimal 2 places to the right. So first class had 4%. Second class had the same frequency, so it would have the same percent. Third class is also 4%. The next class had a frequency of 8. And I know a lot of you have already grabbed your calculator, but if a frequency of 1 is 4%, then what's a frequency of 8 going to be? 8 times 4%, 32%. A frequency of 12 would be 48%, and a frequency of 2 would be 8%. How could you make sure you didn't just make a math error punching on the calculator? What should those percents add up to? 100%. Let's see if they do. There's 12 and 32 is 46 and 48 is 94 and 92. 92 and 8 is 100. Let me double check that. 12, 44, 92, 100. 100%. So without that middle column, which I only copied so I didn't have to flip over and look at the other side of the paper, without that middle column, that is a frequency table, a relative frequency table. And we could make a relative frequency histogram. I don't think we will. Just to save time, it's going to look just like the other histogram, but rather than having the frequencies up the vertical axis, it will have the relative frequency or the percents. So the top bar would need to go up to the highest percent is 48%. If your vertical axis was just labeled, say, 0 to 50%, that would be good enough. All right, let's talk about one other kind of frequency distribution. We've talked about a plain old frequency distribution, a relative frequency distribution, and now we want to talk about a cumulative frequency distribution. Remember when I said you can just look at the frequencies for each class in the cigarettes and tell that a vast majority of the cigarettes had 0.8 or more milligrams of nicotine, I was really giving you a preview of the cumulative frequency distribution then, rather than just telling me how many people had pulse rates between 60 and 69, how many people had pulse rates between 70 and 79. I want to know what percent of people have pulse rates less than 70. Not percent. How many people have pulse rates less than 70? How many people have pulse rates less than 80, less than 90, all the way up to everybody had a pulse rate less than 130? So just start with less than the lower limit of your second class. Everybody that fell in that first class was below 70. So the first class in your cumulative frequency distribution would be less than 70 is this 12 people. Less than 80 would be this 12 people plus this 14 people. Less than 90, just add up all three classes until you get to the very last class, less than 130. Everybody was less than 130. So the cumulative frequency on that last row should include everybody. Here are all three frequency tables for the pulse rate. The very simplest frequency distribution, the relative frequency distribution just converts all of these to percents of total, and then the cumulative frequency distribution, which doesn't have the upper and lower class limits, but it's just less than 70, less than 80, less than 90, and so on. So let's do the same thing with our cigarettes. Use the same data to construct a cumulative frequency distribution. Well, right above that, we have our frequency distribution. No brand of cigarette had less than 0.2 milligrams of nicotine. Only one cigarette had less than 0.4. So that's going to be our first class. Our first class will be less than the second class, or less than 0.4 milligrams of nicotine. And then just use your other lower class limits. We'll have less than 0.6, 0.8, 1.0, 1.2. Now, if we stop at less than 1.2, we're going to miss some brand of cigarettes that had 1.3. We have to go one class beyond that to less than 1.4 so that all of our data values falls into one of those classes. How many cigarettes had less than 0.4 milligrams of nicotine? Only this one in the first class. That was the only brand that had less than 0.4 milligrams of nicotine. How many had less than 0.6 milligrams of nicotine? Well, here's 0.6. There are two lower than that. How many brands had less than 0.8? Well, this one, and this one give us 3. How many less than 1.0? These 3 plus these 8 Gives you 11. How many less than 1.2? These 11 that we've already counted, plus these 12, 23. And how many less than 1.4? All of them. In a cumulative frequency distribution, you're adding the frequency for the cumulative frequency for the previous class to how many fell into the next class. Everybody falls into the last class. If not, then you don't have your last class labeled correctly. No. All right. So what can we tell by looking at these frequency tables and these histograms? Cigarettes are bad and your heart beating is good. That's what you can figure out. Later we'll make a big deal of a normal distribution. This section just mentions it briefly, gets it in your head, and says we'll come back to it later. But a normal distribution is also called a bell-shaped distribution. And I bet a mental image pops in all of your heads when I say the bell-shaped curve. It starts low, reaches some peak, and then goes back to low, relatively symmetric. The frequencies start low, increase to one or two high frequencies, decrease to a low frequency. When data fits that shape, you say the data is from the normal distribution. And when you're looking at the graph, you say that's a bell-shaped curve. The distribution is approximately symmetric with frequencies preceding the maximum up to the peak, looking pretty much like what comes after the peak. You could fold it in half and the two sides would match up pretty closely. Was that the case for the, here's a picture of the histogram. Was that the case for the histogram of pulse rates? No, that's not even close to a bell-shaped curve. Those pulse rates are not normally distributed between 60 and 129 beats per minute. It's not true for the amount of nicotine either. If you look at that graph on your paper, that is not bell-shaped. It's not symmetric. It's skewed much more toward one end than the other. There were very few low amounts of nicotine. Most had the high amounts of nicotine. But if you look at this other picture did I put it on here or just the other page? That represents some data that is normally distributed. Starts off with a low frequency, reaches one or two high frequencies, and then tapers back off, roughly a mirror image of the left-hand side. So you could look at that histogram and say, that's from a normal distribution. If you look at the graph, you say, that's a bell-shaped curve. Now, I think there's one other graph that I put on the handout. Not graph, but a frequency distribution. And I put a couple notes here about the normal distribution, the ones I've already mentioned. This table 2.5 in example 2 gives a frequency distribution for IQ scores. IQ scores are normally distributed. An average IQ, do you know what number on the Wechsler scale corresponds to an average or mean IQ? 100. 100 is average. Below 100 is below average. Above 100 is above average. They're normally distributed it makes sense to say most people are average. That's kind of the definition of average, although it's not true to say you have the average number of feet. Remember that? Average number of feet? You have the median number of feet, but not the mean number of feet. Average IQ score is 100, so the vast majority of the population their IQ falls between 90 and 109. This is out of, I think, 1,000 people. Out of 1,000 adults, almost half of them fall in that one class. And then a class below and a class above also have close to the same number of people. 2 classes below and 2 classes above have very close to the same number of people. These are your Mensa folks right here, your geniuses. So you can look at a frequency distribution or a histogram and determine whether or not it's from a